Stefano, thank you so much for joining me today.
Thank you for having me.
Let's start with the core concept of what we'll be talking about today. And it's a pretty big jump from the traditional large language models that people are familiar with. So to start with, can you talk about when we say LLM, what is that? Like, what is the autoregressive model? And then from there we can go to diffusion LLM, which you started.
Of course. Yeah. So when we think about LLMs, most existing LLMs like ChatGPT, like Claude, like Gemini are so-called autoregressive. And what this means is that they generate text. Let's say they answer your questions or they write code for you in a very specific way. They generate it, as you can see, whenever you interact with ChatGPT, for example, they generate answers one word at a time, left to right. On the other hand, you've used maybe a video generative model or an image generative model. Those kind of generative AI solutions are based on something called a diffusion model, which works in a very different way. The object that you're giving to the user is not created left to right, one pixel at a time, but it's created through a refinement process where you start with a rough guess of what the answer should be, and then you refine it by removing noise, by fixing mistakes until you get to a beautiful image or a beautiful video that you give to the user. And what we're doing at Inception Labs is we figure out a way to apply that technology, diffusion technology, to text and code generation, which was previously and typically approached using an autoregressive approach. And so when we generate code for our users, for example, we don't generate it left to right, one token, one word at a time. Instead, we generated the whole thing in parallel. We start with a rough guess of what the code should be, and then we fix it using, again, a deep neural network. We fix mistakes, we make it better until we finally generate a solution that we can give to our users.
That's amazing. Even the concept, because as humans, one would think that we write from left to right. We think one word after the other, and then you write it. So to go from here to saying that, hey, we'll generate a rough outline first, which means the 76th word and the second word, there's a chance that they'll co-appear. So intuitively, how do you explain it to somebody if you're explaining to somebody who's new to this, how does it work, or even why does it work?
Yeah. So it's similar to the way you would, perhaps write a document by first starting out with an outline, or maybe you start with a few bullet points, or here's what I'm gonna say at the beginning, and then I'm gonna jump into this paragraph and concept, and then I'm gonna move on maybe to the conclusion. And then you start with an outline, and then you refine it by going through multiple rounds of edits until you get something that you like. And so it has a similar flavor in the sense that you start with a rough guess, which is typically pretty bad, and then you refine it until it gets to the final answer, which is the one you're actually going to give to the user. Another analogy could be sculpture, right? When you're sculpting, you're creating a sculpture, you start with a block, and then you remove pieces and you refine it until you get a beautiful object at the end. It has a little bit of the flavor of the process that we use in a diffusion language model.
Right. And now that we are entering perhaps a post LLM era, LLMs will still continue to do great things, but what ceiling or what limitations are we hitting with autoregressive LLMs? Is it cost, latency, reliability, maybe a combination?
Yeah, it's always about those three things. I think it's always about the kind of trade-offs that you get between quality, cost, and speed. And you see that there's always trade-offs, and you typically cannot get all three at the same time. And if you want the highest possible quality, then the models have to be extremely large, which means that they are slow and that they are expensive. And if you want really quick answers, because maybe you want to interact in real time, or you're building a voice agent, then you might need to use smaller models, which are not as high quality, and maybe they're cheaper, but there's always a trade-off between those three things. The reason we've been building diffusion language models is that they are allowing us to kind of like shift the Pareto frontier of the kind of trade-offs you get between those three things. And we can achieve models that have, let's say, same quality as an autoregressive model, but it might be 10 times faster, or it could be 10 times cheaper to serve, because we can make better use of GPUs, because in a diffusion model, the key limitation of an autoregressive model is that it's very sequential. If you think about generating text left to right, one word at a time, it's by definition something sequential where you have to go through essentially a for loop, and there is no really easy way to parallelize this kind of computation. A diffusion language model is built from the ground up to be extremely parallelizable. A diffusion language model, it's able to modify many things at the same time. And so it's taking full advantage of GPUs, parallel processing hardware. And that's why it can be much faster and much more efficient to serve in terms of like the cost per token that we can provide to our users.
You've been very early on diffusion research, and you founded Inception to commercialize this offering. What what changed in the last maybe 18 to 24 months that has made diffusion possible, or at least diffusion models for language, commercially viable?
Yeah. So my story, I've been doing research in generative AI for a long time. Back in 2019, the world of generative AI for image generation was dominated by generative adversarial networks, GANs, right? Everybody was building GANs, and that was the best approach. And with my students, we started working on a different approach, score-based diffusion models, and we were able to show that, yeah, there is a better approach to generate images using this kind of like coarse-to-fine generation guided by a diffusion process. The community quickly realized that approach was superior. And very soon after, we started having stable diffusion, Midjourney, and everybody basically switched to the stack that is still powering the best video and image generative models that we have today. In the last 4 or 5 years, I've been trying in my lab at Stanford to figure out a way to get this diffusion-based approach to work, not just on image and video generation, but also on text and code, and kind of like more discrete objects. And it's been challenging, but back in 2024, last year, we had a breakthrough. We figured out a way to essentially extend the math that would typically require continuous objects to the discrete space of text and code. We published a paper kind of like showing that for the first time, diffusion language model were competitive with autoregressive models at very small scale, like a GPT-2 scale in terms of quality, and then they were significantly faster. And so, that paper won the best paper award at ICML, the top machine learning conference. It was kind of like recognized by the community as being like a research breakthrough. And I was very excited about the results that we were seeing. And so I decided to scale things up and build a company to really do all the work that is needed to take the research prototype and turn it into something that is now serving production traffic, and people are using to build really cool apps and delivering some really interesting new experiences to users around the world.
Right. And especially in a world where AI is now attracting billions of capital and everyone's working on it. So it's hard to truly show like an order of magnitude difference in performance. It's very difficult, and yet I think diffusion LLMs have shown that it's not like 11% better. It could be much better. Now, so I want to dive into the mechanics, the architecture, and how it actually works. Maybe let's start with parallel refinement. How does it work? How does it differ from token to token prediction that we are all familiar with?
Yeah, so under the hood, there is still a neural network. So that doesn't change. And the architecture of the neural network, it's something that you can iterate over. We're using a lot of architectural choices that are not that different from what's used in the traditional autoregressive world. And so we're still using tension, we're using transformer-based architectures to define the underlying neural network. Although, we've done experiments using state space models. And so it's possible to kind of like different kinds of neural networks, but the key difference is really in the way the neural network is trained. So instead, in a traditional autoregressive model, the neural network is trained to predict the next token. That's the only thing that you care about. You train the model to predict the next token. And then at the inference time, you just roll it out. The user gives you a question, and then you ask the model to predict the next token, then you fit it back in, the token after, you fit it back in, and you keep going. A diffusion language model, on the other hand, it's trained through denoising. And so the neural network is trained to fix mistakes. So you start with clean text or clean code. You essentially intentionally introduce mistakes, and then you train a neural network to fix the mistakes because you know the original answer. You know what is changes you need to do to fix the mistakes because you introduce the mistakes yourself, and you pre-train essentially this neural network to fix mistakes. And then at the inference time, the way you generate an answer is you start with something that is completely wrong. You start with something that could be completely random or with a very bad guess of what the answer should be. And then you ask the network to fix some mistakes in here. And then you take the answer of the network and you fit it back in and you say, fix more mistakes. And you keep going until you get to a good quality answer. And that's when you stop.
And that's amazing. And when it comes to diffusion for language, what does step mean? And also, how many steps do you typically need for a high quality output that a average user is happy with?
So a step basically typically refers to one forward pass through the neural network, which will produce an improved version essentially of the input. It will fix some of the mistakes. And so that's the key kind of like iteration. The key difference compared to in an autoregressive model, you basically need one step for every token you want to produce in the answer. Every forward pass through the neural network will only ever give you one token. In a diffusion model, each forward pass through the neural network will be able to modify multiple tokens. And so for the same cost, you get potentially more, because if you can fix more than one token, then you get a benefit. And so then the number of steps that you require depend on a lot of things. It depends on how good the denoiser, how good the neural network is. It depends on the kind of inference algorithm that you use. But there's a lot of secret sauce that goes into reducing the number of steps. But what we're seeing is that in practice, you don't need that many steps. And that's why our diffusion language models, Mercury models, as we call them, they're significantly faster than autoregressive models of comparable quality.
At Inception, you built your own model, Mercury, and so many things you had to do to make it production ready. So if you had to pick the hardest engineering challenge to make it production ready, what was it?
I mean, there was a lot of R&D required in terms of like trying to figure out what is the right recipe to train the model and use it at the inference time. There were quite a bit of challenging in terms of like scaling up the training. Another big challenge was actually developing which is more really engineering, not necessarily R&D, but a big engineering challenge was developing our own serving engine. So as you know, whenever you want to serve an autoregressive model efficiently to handle production traffic, you would use a system like VLLM or SGLang or TensorRT. That is basically a system that is designed to serve an LLM efficiently and handle queues and handle the GPU resources as efficiently as possible. And in order to serve diffusion language models efficiently, we have to develop our own version of something like one of these frameworks. And that was a pretty significant kind of like engineering work that we did. But it was very important to be able to actually get performance on production traffic.
Right. And if you had to pick, what has surprised you the most when you went from your research to like commercial scale models?
It surprised me how important data was. I mean, I knew that data was important. I've heard about it, but in the academic setting, we were always able to kind of like get around it and just use standard data sets and then kind of like do academic style comparisons where you say, oh, I'm going to treat the same, bunch of different models on the same data, and then I'm going to see which one is better. But then in the real world, the kind of data that you use for training the model, the quality of the data, the filtering that you do is really, really important. And so, that was one of the interesting lessons of like the importance of the data in the real world.
Right. And we've talked about areas where diffusion LLMs are better than autoregressive, like it can be X faster or 10x cheaper. Now, what are areas where it's still lacking, or perhaps you made a trade-off to make it ready, but what are areas where it's still catching up to autoregressive models?
So existing diffusion language models are not capable of reasoning. That's one thing that has enabled autoregressive models to drastically improve the quality of the answers. So that is one thing that we're working on, which is basically enabling diffusion language models to have reasoning capabilities, which allows you to do and solve tasks that require planning, require reasoning. It kind of like opens up a number of application areas where the existing diffusion language models are not suitable for. Another thing that doesn't quite exist today is, which is a little bit ironic, but existing diffusion language models are not multimodal. Even though diffusion models are the best approach for image and video generation, right now our models are text only, so they do not support image inputs or image outputs. But it's something that we're very excited about building. We think we're going to get some great results just because we know diffusion works so well on those modalities. Now that we know how to get text to work, it should be relatively easy to be able to build a multimodal kind of single model that can capture all the modalities and learn across different modalities. We're actually very excited about that, but it's something that does not exist today.
I mean, that's very helpful to know. And when it comes to evaluations, evals, do we is it fair to use the exact same metrics to compare all the other LLMs with diffusion LLMs, or do we need some new evals to make it at least fair?
We can use the same evals. I think, as you know, I mean, there is a variety of different evals, and people argue what is the right one. And you might care about different subsets of those evaluations depending on what is the task that you're trying to solve and what is the application that you're trying to support. But the same sort of set of evaluations can be used to benchmark diffusion language models. We've benchmarked our models on standard evals. We've had our models evaluated by artificial analysis. They have their own kind of like set of benchmarks that they think are representative of the level of intelligence of different models, and they involve a variety of tasks like following instructions and math and code. And so we've been able to benchmark diffusion language models on the same set of tasks as autoregressive models. And that's why we can confidently say that the quality of diffusion language models is already matching the one of the best speed optimized autoregressive models, including from frontier labs. And so that's how we're confident about the quality of the models. And speed, again, speed is the other metric that matters, and that is easy to measure. I think at the end of the day, users care about end-to-end. They can see how quickly do they get the answer, how quickly will their agent complete the task. And so again, that's a very fair, it's a very good metric to use, and we do very, very well in terms of those benchmarks as well. As you mentioned, it could be 5 to 10x better than comparable autoregressive.
And if I'm a developer who's building AI applications and I'm familiar with using OpenAI, Gemini, Anthropic's offerings, what's different for me if I have to integrate a diffusion LLM into my product? Prompting, tool calling, streaming, like how should I think about it?
Yeah, so we've done all the work to make it very easy for developers to use diffusion language models. So we're currently serving them in an OpenAI-compatible API. So you can literally just swap out API key and the URL, and everything should work out of the box. We support streaming. We support tool call. So most of the features we support structured outputs. So most of the features that are supported by existing autoregressive models and through an OpenAI compatible endpoint, we do support them. And so it's very easy to give it a try, to swap it out. Of course, the models are different, so you might need to adapt the prompts a little bit, but it's usually not that different, and people are able to enjoy the speed and the quality and the cost of diffusion language models very easily just by changing an API key in at the endpoint.
That's wonderful. I think that's the best developer experience, is that when I don't have to do anything, I just swap out a line and it starts working. I do want to shift to the economics of this paradigm, economics and infra. Now, help us quantify the cost curve. As you work on this more, obviously things will get better. Where do you see cost per 1,000 tokens and a cost per request trending. As you do more of this, more people start working on this, and you introduce all sorts of engineering optimizations.
Yeah, so costs are going down, and that's a good thing. I mean, I think that will just mean people will use AI models and LLMs more. What's exciting to us is that diffusion language models make better use of the flops that are provided by GPUs. And so, because they're built from the perspective of, let's try to come up with an inference algorithm that is optimal for what GPUs are good at, which is matrix multiplications. And so what we are seeing is that we are, again, Pareto dominating what's possible with autoregressive models. And so for the same speed, we can reduce the cost, or for the same cost, we can increase the speed. And so we're excited about this technology, because eventually it's all going to be an inference game. Because our technology is more efficient on GPUs, we think we're going to have an advantage that it's going to be impossible to replicate with an autoregressive model that is fundamentally sequential and cannot be parallelized beyond a certain point.
And speaking of the hardware, what hardware and runtime stack has been effective for you so far?
We are building everything on NVIDIA GPUs. And so at the moment, our stack is kind of like pretty optimized for that backend. It doesn't have to be. In principle, we could run our models on different accelerators. We haven't done the work of actually writing the kernels and optimizing the serving engine for other backends. But in theory, it's entirely possible. So yeah, what's an exciting thing about diffusion language models is that we can basically get the speed that you would get if you were to use one of the, high inference chips, like, the Groks, the Samba Novas, the Cerebras. You can get to those kind of speeds, but you can get them on just commodity GPUs because we have a better algorithm. So all the improvements are at the software, at the layer, and not at the hardware.
Now I want to move to the market and the competition here. So there are, in this AI world, we have big frontier labs. That is small, fast models. That is large open source models, and other like autoregressive architecture. So who do you view as the most direct competition to diffusion LLMs?
Yeah. So, I mean, of course, there's kind of two buckets. There is the autoregressive models, and we're competing head to head with autoregressive models at the moment. We are winning in terms of like the speed optimized kind of setting for autoregressive models. So, in a lot of applications where people care about speed, so where there is you're interacting with a human in real time, or things where you really need to be able to give an answer very, very quickly. What we're seeing is that we can match the quality, we can be much faster, or we can put in a bigger model that preserves the original latency budget but could give you higher quality answers. Then there is other companies that are building diffusion language models. We know there's been an announcement from Google, Gemini Diffusion. There's been an announcement from ByteDance about a diffusion language model that they've built in-house. It's exciting to see that the space is picking up speed. We're still the only ones that have something that is serving production traffic, both Gemini Diffusion and the one from ByteDance. They were more like prototypes. It's a demo that you can play with maybe, but they've not been providing API access to the models. They're not serving production traffic. And so we're still far ahead from that perspective.
And obviously, there's always a way to carve a niche where, for example, at a time when OpenAI looked like they're going to win everything, suddenly Anthropic's Claude somehow was better at coding, and suddenly now everyone just uses Claude for coding, and that they carved a niche. So where will diffusion most likely win in the next 12 months? And is it voice? Is it code gen? Is it agentic systems? Perhaps something else where there's a clear advantage?
We're seeing a lot of traction and really exciting results in some parts of the if you think about coding, it's a big space, and there's many different kinds of use cases that go all the way from simple autocomplete all the way to complex agentic workflows. we are seeing a lot of really good results and traction for, like editing style applications of LLMs in the coding space. So autocomplete, but also like next edit, auto edit, apply edit, chat edit, these kind of things where you're asking the model to make changes to your code base based on some instructions or based on previous changes or just based on the context of what's around it. And we are seeing that diffusion language models, and Mercury specifically, is the best model in terms of quality. There is something called Copilot Arena. It's like an academic benchmark that people use to kind of like LLM Arena, where people kind of compare the quality of the answers that come from language models, and the answers are scored by developers, by real people. Mercury models are number one for quality. They're number one for speed. We launched with Continue, the dev, one of the leading open source coding IDEs with a lot of AI features. The default for next edit is a Mercury diffusion language models. So we're seeing a lot of traction in that space, and we're very excited about it. Uh, I think the intuition is just that if you think about, you were saying before that maybe we tend to think about writing as being this left to right process. If you think about code, I think it's a lot less left to right. Like if you think about a big code base, like there's not necessarily an order between the files, and even the way you write code involves a lot more back and forth and edits and changes. And so that was actually one of the main reasons we started out with code. We felt like that's going to be a space where diffusion could be really, really good. And indeed, we're seeing really high quality on those tasks with the next generation of models that we're building and training. And we have some prototypes in house, like the reasoning enabled models. I think we're going to be able to capture a bigger slice of this market. And I wouldn't be surprised. And I think it's very likely that diffusion models will become the default for a lot of the coding use cases in the next 12 to 18 months.
That's actually a great segue into my next question is, let's say that we're looking into the future, we're at a future point where diffusion becomes the default. Now, with that being the case, what second order effects should infra developers expect? Like, serving patterns, caching, evals, cost, everything. Like, what should they expect to do in this new world?
Yeah, there's going to be a lot of changes, I think, lots of opportunities for, enabling different kinds of experiences, changing the way these models are used. At the moment, we're still kind of like trying to keep things backward compatible as much as possible so that it's easy for people to build and they don't need to make too many changes. But you can imagine a future where people interface with these models in a different way because of the fundamentally different approach that they use to generate text and code. We know that diffusion models are generally more controllable, they're easier to constrain. So I'm pretty excited about new things that we're not even thinking about and new ways of using these models. And the moment, we have these prototypes, we get them in the hands of developers and the technology matures, I think there is going to be a lot of exciting opportunities in terms of like different ways of interfacing with the models. On the serving layer, I think that we have our own serving engine. I'm sure there's many more optimizations that can be built on top of that. So I'd expect that if more people start building on this technology, there's going to be even more improvement in terms of like the efficiency, the speed, and the reduction in cost. An interesting question is, how should the hardware change? I think which I know the major hardware providers are already thinking about, like how should our hardware evolve and change to better support these kind of LLMs. It's all about, if you've seen Jensen's keynote, it's all about throughput versus latency, and then how can you use the NVIDIA GPUs to kind of like get the best speed versus cost trade-off when you serve LLMs. Now, the moment you change the inference algorithm, and you have something that is fundamentally more parallel, that changes the way you build GPUs, the number of flops that you need, and how much you rely on memory bandwidth and the amounts of memory that you need. So the game changes, and so it's going to be exciting to think about these effects on the whole stack from hardware all the way to the applications.
Amazing. I have one final question before we go to the rapid fire round. And it's a two-part question. Part A is what's coming next at Inception over the next 12 months. And part B is outside of your work at Inception. What AI advancements are the most exciting to you?
Yeah, at Inception, the next big thing is going to be a reasoning model. So expect that to come pretty soon. Based on internal results, we're able to significantly increase the quality of the answers and the intelligence score as measured by index and other benchmarks that people care about and use to measure how good these models are in a variety of important real world tasks, software engineering related tasks. So expect big improvements in terms of quality while keeping the big benefit of giving you really quick answers, which is super exciting. I think it's going to enable a different kind of user experience. It's going to enable agents that are even more complicated. Lots of exciting stuff happening there. And multimodal, that's another thing that we're also, as I mentioned, very excited about. I think there's a lot of opportunities there, and both on the input side, computer use is another setting where latency is super important, but being able to actually process not just text, but also the whole content on the screen is very important. And so we're excited about building that capabilities into diffusion language models. And then, of course, generation. We know diffusion models are the best models for generating images, video. So building a foundation model that can handle all different modalities on a diffusion technology is super exciting to us. More generally, as a field, I'm pretty excited about self-improvement, recursive self-improvement as a thing that might pick up speed in the next few.
Amazing. All right. With that, we're at the rapid fire round. I'll ask a series of questions and would love to hear your answers in 15 seconds or less. You ready?
Go for it.
Question number one. What's your favorite book?
Probably If on a Winter Night a Traveler by Italo Calvino. It's a very unique book, probably one of the most very meta. If you haven't read it, it's highly recommended.
Oh, amazing. I will pick it up. All right. Next question. Which historical figure do you admire the most and why?
Say Claude Shannon. I think he was well, ahead of his time, and he was basically building LLM, thinking about effectively LLMs well before anybody else.
100%. I'm a huge fan. Next question. What's the one thing about diffusion language models that most people don't get?
Most people think that it's still sort of like a research, kind of cute research idea, and that technology is not mature enough, but that's not the case. I think it's already proven, it's already serving production traffic, and it's going to be the future.
What separates great AI products from the merely good ones?
Only the capability to adapt to the users. You don't want the users to adapt to the AI product. You want the AI to adapt to what users want. And I think that's really the thing that makes really exceptional AI tools.
Right. What have you changed your mind on recently?
I guess the importance of data, quality of data.
What's your wildest AI prediction for the next 12 months?
I think we're going to see some cool models and results enabled by recursive self-improvements. So yeah, models that improve themselves.
All right, final question. What's your number one advice to founders who are starting out today?
It's all about people. People is what makes for successful businesses. People is, the people and relationships. That's the number one most important thing to think about and worry about.
Right. Stefano, this has been a brilliant discussion, and I think you're one of the very few people who actually truly know how diffusion language models work, and you're bringing it to production. So I'm really glad we got a chance to talk, and thank you for sharing your insights.
Thank you for hosting me. It was a really fun conversation. Thank you.
Perfect. Give me